Hi everyone, in this lesson we're going to do another set of semantic trees. This time I'll make sure that the sentences use names or individual constants, since we didn't see that last time. And these are going to be pretty simple sentences. This will be a simple problem because I really want to focus on those names. So here's our first sentence: for all x, L, x, A. That might say something like, everybody loves Albert. And then here's our second sentence: for all x, L, A, X. And that says maybe Albert loves everybody. So we're going to learn how to work with those names. But what I really want to do is show that those two sentences are not quantificationally equivalent. Two sentences are quantificationally equivalent if they have the same truth value on every interpretation. So wherever the one's true, the other one's true. Wherever the one's false, the other one's false. But to show that they're not quantificationally equivalent, we have to show an interpretation where the two sentences vary in truth value. I'm going to start in a kind of an odd place. I'm going to start with an interpretation that has a one-element domain. Okay. Part of the reason I'm going to do this is because it actually will not work out, but bear with me. So we're going to, in addition to specifying the universe of discourse, we will have to specify the extension of the two-place predicate L, and we will also have to assign a denotation to the name A. Now, one of the nice things about working with a one-element domain is it makes your denotations very easy to deal with. If there's only one object in the universe, then the name A denotes that object. And in fact, all names will denote that one object. That's just the semantics of naming. Names have to single out an individual thing from the universe of discourse. So when you have a name, and there's only one thing in the universe, that thing is the name's denotation. We are going to leave blank for now the extension of the predicate L, and we'll work that out with our interpretations if we can. So, with our semantic trees if we can. So let's come back over to our sentences. These are both generalizations. They're universal generalizations. Those universal quantifiers are the only logical operators. And so, since they're generalizations, our semantic tree method tells us that we must branch to their instances. Okay, so we will branch a universal generalization to all of its instances. There's only one object in the universe, so there will only be one instance. We're going to drop that quantifier, replacing the variable x with the number 1. I'm going to come over here, and we're going to drop the universal quantifier again, and we're going to recopy, replacing the variable with the number 1. So those are going to be pretty slender trees because they only have one branch each. Okay, so next step would be to replace the denotation of, the name A with its denotation. So we're going to branch under L1A, and we're going to copy it down again, except we're going to replace the name A with the number 1. I'm going to come over here to LA1, replacing A with its denotation becomes L11. Okay, so if we, I'm just going to change font color here, or my pen ink color. If we, this is the part that's just trial and error, suppose we plug a T in under L11. What are the implications of that? Well, if L11 is true, then L1A is going to be true because A is the name of the number 1. And then we'll see that this universal generalization has all true instances. All of its instances are true. There's only one instance, but they're all true. And that means that what we're dealing with is a true universal generalization. Okay? So that's one of the implications of putting a T under L11, is that it goes right up the top to the top of this tree. There's another implication of putting a T under L11, and that is that when we see L11 on this other tree, we have to put a T under it too. We have to. It's not a choice. Well, if L11 is true, then LA1 is true because A is the name for number 1. And then look here, this universal generalization has all true instances, so it's going to come out true as well. And that's fine. That's all perfectly good, except that it doesn't prove what we wanted, which was to show that those two sentences are not quantificationally equivalent. So we are going to have to do some more work, and this is going to make the problem a bit more tricky, but it's also going to make it a little bit more realistic. So what we're going to do is write those sentences down again. So for all x, LXA, and for all x, whoops, excuse me, so as I was saying, and for all x, LAX. So this time we're going to increase the size of the universe. We'll just put 2 objects in there. And again, we're going to come back to it. We'll fix the extension of the predicate L and the denotation of the name A. And at this point, we're not going to assign anything here because we have, in some sense, choices how we construct this interpretation. What are our choices? Well, the choices are 1 or 2. We can assign the name A. We can assign the number 1 to the name A, making 1 the denotation, or we can assign the number 2 to the name A, making 2 the denotation. There are 2 other things we want to mention here very quickly. You can't leave the denotation blank. If you did, no, that little lowercase a would not be a name. Names have to name. And we also can't put both objects, 1 and 2, as the denotations of the name A. Names uniquely specify. And if they don't do that, they're not names. So when we come back over to our trees, again, we're dealing with universal generalizations. And universal generalizations branch to their instances. In this case, since there are 2 objects in the universe of discourse, we're going to have 2 instances, 2 branches. So what we're going to do is drop the quantifier for all x. I'm going to recopy this expression, LXA, at the bottoms of both branches with 1 change. We're going to take that x out, and we're going to put a 1 in for it here on this branch. We're going to take that x out, and we're going to put a 2 in for it on this branch. Okay, so let's hop over here to our other universal generalization. We are also going to branch under it. I'm going to drop that quantifier for all x, and we're going to recopy the quantified expression, LAX. And we're going to do it twice. On the first branch, we'll write LA1, replacing x with 1. And then we'll write over here LA2, replacing that x with 2. Okay. So if we look at these points on the trees, we can see that there is no other logical operators. There are no quantifiers or connectives. So in a way, we're at the end. However, we do have these names still hanging around, and we want to replace them with their denotations. So let me show you something that you shouldn't do. Okay, but it's a mistake to do this, and I've seen it, so I want to bring it out. So you might find yourself tempted to branch under these things and then write L11 and write L12. You might feel tempted to do that. But what I want to just point this out, why this is a mistake. What you're doing is you're treating this name as if it were a variable. So you're saying A could be 1, it could be 2. But on any one interpretation, the name A actually has to uniquely specify an individual object. So actually, it doesn't range over the objects in the universe of discourse the way variables do. Variables vary in value. They can take different things as values. The names, which are also sometimes called individual constants, have a constant value. They don't vary. So this is a mistake. It's a tempting mistake. It's an understandable mistake. But it's a mistake, and you don't want to do that. So let's come back to our black ink pen. Less traumatizing to look at that. And then we're going to come back under these branches. We've got to do something with that name A. We've got to do something with it. So here's what we're going to do. We're going to do a little trial and error. We're going to plug something in here, and we're going to see what happens. That is part of the semantic tree method. So let's suppose that we assign the number 1 as the denotation of the name A. What we're going to do then is come to all of these branches and just copy down what we already have, except we'll replace the A with a number 1. Okay, so tentatively at least, and this might not work out, tentatively at least, the name A picks out the number 1, right? So now we're ready to start assigning some truth values, which again, trial and error, see what happens. Let's see what happens if we make L11 true, just like we did in the last attempt at this problem. If L11 is true, then L1A is true, because A is just the name of 1. And if L11 is true on the tree on the left, then L11 is going to have to be true on the tree on the right. And that means that the sentence LA1 will be true, because A is the name of the number 1. So far, so good. We do not get to copy this T up here yet. A universal generalization to be true has to have all true instances. These two universal generalizations have at least one true instance. So let's play around and suppose that we put a T here on the top of this branch. We want this universal generalization to be true. So far what we've done doesn't stand in the way of that. It's got a true instance. That doesn't stand in the way of it being true. But if we want it to be true, all of its instances have to be true. So we're going to just follow that through. L2A must be true. And if 1 is the extension of A, then L21 must be true. So we've got a T now and another T under the bottom portion of a tree. We want to make sure that we don't see L21 anywhere else. So we'll come over here and look at here. We don't have L21, we have L12. So we don't recopy that T. Again, remembering what we're doing, we are trying to prove that these two statements are not quantificationally equivalent. We want them to have different truth values then. So, can we make this universal generalization false? Well, it has two instances. One of those instances is true, and that tells us that the other one is going to have to come out false. LA2 has to be false. And then that sort of computes downward. If LA2 is false, and 1 is the denotation of A, then L12 is also false. Okay. So we have complete trees. They're fully worked out. We have T's and F's at every node and at the very top. And it tells us what we want to, it shows us what we want to see. We want to see that one of those statements came out true and the other one came out false. So how do we fill in the rest of the interpretation? We get it all at the very bottom portion of the tree, okay, at the very bottoms of those branches. So we see a T under L11. That tells us that the pair 1, 1 is in the extension of the predicate L. That's an ordered pair 1, 1. We see a T under L21. And so that tells us that the ordered pair 2, 1 is also in the extension of the predicate L. Okay. And then we see L1, 2, and under it we have an F. Okay, that's good information. It tells us we have to leave the pair 1, 2 out of the extension of L. So we're going to go ahead and close off the extension of L. So what we have here then is an interpretation, and on this interpretation, these two sentences have different truth values, and our semantic trees prove that these sentences vary in truth value on this interpretation.